Hey St. Mary Grade 8s, it's Mr. McHenry back with another math lesson on our unit in probability. Today we're going to talk about tree diagrams, which is an important tool, especially when you're looking at something that has two or more events or activities in it. So for example, you flip a coin and then you spin a spinner. Or you spin a spinner and then you roll a cube, and you want to find the outcomes. So we can use a tree diagram to find the probability of a particular outcome. So we're going to get right into an example today. The example is player A, Isabella, and player B, Kishni, play the spin sum game, where each player spins the spinners and once. So we have spinner number 1, which has a 1 and 5 on it, and then they spin spinner number 2, which has 2, 3, and 4 on it. So for example, Isabella would spin the spinner and lands on 5, and then she would spin the spinner and it lands on 3. Well, what results? Well, if the sum of their spins is an even number, player A, Isabella, gets 1 point. If the sum of their spins is an odd number, player B, Kishni, gets 1 point. So in this example, which we just talked about, Isabella spun a 5 and then she spun a 3. So that's an even number that adds to 8, and so she would get the point. So to help us come up with all the outcomes and then be able to calculate probability, we want to create a tree diagram. And I've put the spinners up here so to help us out here. So what we want is we want to know all of the outcomes. Okay, and we have the second activity, which is activity number 2, which is spinner number 2. And then we have activity number 1, which is spinner number 1. All right, and just a note before we continue on, when you're doing tree diagrams, you want to give yourself like the whole page to do a tree diagram. Lots of space, because sometimes if you don't give yourself lots of space, there's many different outcomes, and then you end up squishing your work and it's hard to know what's going on, etc. So please, lots of space when you're using tree diagrams. So we want to create a tree diagram for this game. So what is going to happen? Well, we're going to put the word start here. And so we start the game. Well, to start the game, one of the players spins the spinner, and what could it land on? It could land on a 1. So it's landed on a 1. Now they're going to spin the second spinner, and it could land on a 2. And that would give a sum of 1 plus 2 is equal to 3. Okay, and the thing about probability is that it's tough to understand sometimes because you have to forget the past. Okay, the past is the past, and it doesn't have any influence on what's going to happen next. So again, we spin the spinner and it happens to land on 1. And this time we spin the spinner again and it lands on 3. So now we have an outcome of 1 plus 3, which is equal to 4. Okay, and we spin the spinner again, it lands on 1. We spin the spinner again, and there is a possibility it could land on 4. So now we have an outcome of 1 plus 4 is equal to 5. Okay, so those are all the combinations to create outcomes that if we spun the spinner and it landed on 1 first. But it can also land on 5. So the spinner is spun, it lands on 5. Well, what else can it land on? It could land on 5 and 2. And that would give a combination of 5 plus 2 and an outcome of 7. It could land on 5 first, and then it could land on 3. That would give 5 plus 3, outcome of 8. And last, it could land on 5 and could land on 4. And that would give a sum of 9. Okay, so we've got all of the outcomes here. And one thing I like to do, because you're going to need to know this when we're calculating the probability, is we're going to, how many total outcomes are there? Well, there are 1, 2, 3, 4, 5, 6 total outcomes. So I always like to write that down underneath. Total outcomes equal to 6. So we're going to write some information down here to help us, because we're going to be calculating some probabilities. So just as we said, there are 6 possible, or I use the word total, outcomes. Okay, and those are 3, 4, 5, 7, 8, and 9. So out of those possible or total outcomes, 2 have even numbers. So there are 2 even number outcomes. And those are 4 and 8. And then we have 4 odd number outcomes. And those are 3, 5, 7, and 9. Okay, so we got our nice tree diagram here. We've got some information. We're going to use that information to help us out. I've rewritten that information up here. Possible outcomes or total outcomes is equal to 6. Outcomes that are even numbers is equal to 2. Outcomes that are odd numbers equal to 4. So now we want to find out the probability of getting an even number. And we're going to be calculating the theoretical probability. So again, in a perfect world, before we play this game, if everything, it was perfect, what's the probability? Or another word is, what's the odds that we would have that? So we use the formula for theoretical probability, which is the number of favorable outcomes. So we're looking for even numbers. So there were 2 favorable outcomes. Those were 4 and 8. So we write 2 favorable outcomes divided by the number of possible outcomes, which was 6, which is the total number of outcomes. That equals 0.333 repeating, which we round to 0.33, which is equal to 33%. Okay, probability of getting an odd number. Again, using theoretical probability in a perfect world, number of favorable outcomes for getting an odd number. Well, there were 4 favorable outcomes. Divided by the number of possible or total outcomes is 6. That equals 0.677 repeating, which is equal to 0.666 repeating, which is equal to 0.667, which is equal to 67%. And you notice here that these 2 percentages, they add up to 100. So that's just a nice little check as you're moving through these to make sure you're on the right track. Okay, always doing little checks along the way. Okay, so now we know the probability of getting an even number is 33% and a probability of getting an odd number is 67%. So is the spin sum game a fair game? Well, no. No, not a fair game. Okay? Because they don't have an even percentage. Because not equal chance or probability. Right? 33% for even is less than 67% for odd. Okay, so it's not a fair game. So we want to make it a fair game. How could we make the spin sum game fair? Where each player has an equal probability of winning. So in this case, There's only 2 players, so an equal probability would be a 50% chance or probability. Well, what could we do? Well, to make the game fair, so player A, which we said was Isabella, she could get a point if the sum of the spins is less than 6. Okay? And player B, Kishni, gets a point if the sum of the spins is greater than 6. So if I bring our tree diagram back and we look at those outcomes, how many of these spin sums are less than 6? Well, we know there's 6 total, and 1, 2, 3 are less than 6, and 1, 2, 3 are greater than 6. So that would make it a fair game because each player would have an equal chance of winning. And what's that chance of winning? That would be 50%. Okay, so Isabella and Kishni agree on this new fair game, and they play the game. So they do the experiment. Okay, so again, remember when we're talking about theoretical, it's a perfect world, haven't done anything, but in experimental probability, you actually do. All right, in experimental, it is not a perfect world. So they actually play, they do the experiment 50 times. 26 of the plays had a sum less than 6, and 24 of the plays had a sum greater than 6. What is the experimental probability of getting a sum less than 6? Okay, so we're going to calculate the experimental probability of getting a sum less than 6, which is equal to the number of times the outcome occurred. So how many times was there a sum less than 6? Well, it was 26. Divided by the total number of trials. How many times did they play the game? Well, that was 50. So we have 26 divided by 50, and that equals 0.52 or 52%. Okay, so 52% of the time out of 50 times when they played the game, there was a sum less than 6. We also want to count the experimental probability of getting a sum greater than 6. And again, experimental probability is the number of times an outcome occurs divided by the number of trials. So how many times was there an outcome with a sum greater than 6? Well, there was 24. Divided by how many times did they number of trials, how many times did they play the game? 50, and that equals 0.48 or 48%. And again, we can do that little mental check here. I got 48 and 52. Those add up to 100%. So I am good with that. So we have an experimental probability of getting a sum less than 6 of 52% and a sum greater than 6 of 48%. And the theoretical probability of getting a sum less than 6 is, well, how many were less than 6? There were 3 favorable outcomes divided by the total number of outcomes is 6, so that's 0.5, which is equal 50%. Again, getting a sum greater than 6, theoretical, is the number of favorable outcomes, which we saw in the tree diagram was 3, divided by the total outcomes or possible outcomes is 6, is equal to 0.5 or 50%. Okay, so when we look at this, we see 52% with experimental versus 50 with theoretical, 48 with experimental, 50 with theoretical. So they differ, okay? And why do they differ? Because we don't live in a perfect world. All right, that's the difference between theoretical and experimental. Theoretical is if we lived in a perfect world, this is what should happen or is expected to happen. When we actually do the experiment or play the game, that doesn't usually happen. Okay, we get a different probability. However, the greater number of times, so the more and more and more and more and more that we play this game, so if we played it like an infinity number of times, okay, which is the biggest number, the more that the game is played, the closer and closer the experimental probabilities will be to the theoretical probability. Okay, so the notes for this lesson will be on D2L if you need to refer to them and help you with your practice questions as well as the practice questions to get you comfortable and confident with using tree diagrams. Take care.